Uncertainty is related to the limits of our ability to make measurements and the idea that the act of measuring something affects the quantity being measured. For example, if we place a cool thermometer in a cup of hot coffee, the temperature of the coffee is altered as it transfers heat to the thermometer. The measuring device alters the quantity being measured. This kind of error in measurement can be corrected if we know the initial temperature of the thermometer, the masses and specific heats involved, and so forth. Such corrections fall well within the domain of classical physics. These are not the uncertainties of quantum physics. A feature of quantum physics goes further. Uncertainty is basic and inescapable. It's just the way nature is. Einstein didn't like quantum uncertainty. He liked to say that he couldn't believe that God played dice with the universe. Quantum uncertainties can be related to the wave nature of matter. A wave, by its very nature, occupies some space and lasts for some time. It cannot be squeezed to a point in space or limited to a single instant of time, for then it wouldn't be a wave. This inherent fuzziness of a wave gives a fuzziness or uncertainty of measurement at the quantum level. Experiments upon experiments at the quantum level have shown that any measurement in a system necessarily disturbs the system by at least one quantum of action, h, Planck's constant. That's the minimum inaccuracy you can hope for in any quantum measurements. I repeat, never zero, but at best, Planck's constant h. Here it is important to distinguish between observing a system and probing it. Back to our cup of coffee. If you passively glance at it and see steam rising from it, this act of measuring involves practically no physical interaction between your eyes and the coffee. The coffee does what it's doing whether you look at it or not. Your glance neither adds nor subtracts energy from the coffee. You can assert that it's hot with no active probing. Placing a thermometer in it is a different story. Then you've gone beyond observing and into probing, for you physically interact with the coffee and therefore affect and alter its measurement. The quantum contribution to this alteration, however, is completely dwarfed by classical uncertainties and is negligible. Quantum uncertainties are significant only in the atomic and subatomic realm. I say this again for emphasis. Quantum uncertainties are significant only in the atomic and subatomic realm. They don't explain uncertainties in your coffee's temperature. Compare the acts of making speed measurements of a pitched baseball and of an electron in a beam of electrons. You can measure the speed of a pitched baseball by having it fly through a pair of photodetectors that are a known distance apart. The ball is timed as it interrupts beams of light in the detectors. The accuracy of the ball's measured speed involves uncertainties in the measured distance between the detectors and in the timing mechanisms. Interactions between the macroscopic ball and the photons it encounters are insignificant. But not so in measuring submicroscopic things like electrons. Send an electron along the path of the ball, and beams of light from the flashlight appreciably probe the electron. Even a single photon bouncing off an electron can appreciably alter the motion of the electron, and in an unpredictable way. To determine the electron's whereabouts with light, the wavelength of light would have to be very short. But there's a problem here, a fundamental one. Short wavelength light can see the tiny electron better, but its high frequency corresponds to a large quantum of energy. This significantly alters the electron's motion. So how about using light of a longer wavelength, which means a lesser amount of quantum energy? The downside to this is determination of its position will be less certain. The act of observing something as tiny as an electron probes the electron, and so doing produces a considerable uncertainty in either its position or its motion. Not only in this simple experiment, but in all others that have been tried. We'll continue with the uncertainty principle in the next lesson. For now, I want to leave you with a question. In what way do the uncertainties of measuring the temperature of a container of hot water with a thermometer relate to quantum uncertainty? Or not at all? Until next time, good quanta.